Okay, so last time you had a little worksheet to work through, where basically on a very simple example, having 2 points that you're trying to fit, you, I hope, realize that by the end of that exercise, you form a linear system to solve for the data fit. And by fitting, what we mean is I want to actually look at the trend. So if I have a bunch of data, I am not necessarily concerned about trying to find a curve that goes through every point. That can be done with polynomials of order that is high enough. However, that's typically an overkill because data in itself always has certain measurement error that comes in with it. Okay? So if you are too concerned about fitting it, you're also fitting that error. And that if you're trying to be too accurate, you're going to basically replicate that error. So most of the time, what we're actually doing, or the data could be just messy and I could have way too many points to have like a decent function going through all of the points. In that case, we're just looking for the trend. And this trend, the simplest trend would be a straight line. Now, straight line, as a model, we describe it with 2 parameters, right? We have a function, y is ax plus b, or in this case, we're calling it a0 plus a1x, just to be easily extendable to higher orders. So I'm now wondering, how do I find those a0 and a1 so that I fit the data the best? Okay? And what you've done in the worksheet is so-called linear, least squares. The idea is to look at the differences in absolute sense between them. Basically, this is my model, okay? So for this point, this is the actual point, and the model would be right here. So for this given x, right? For this given x, this is my actual data point, this is my model, and this model is a0 plus a1x. The difference between them, the error, is given as e. That's the actual data point minus the model. Okay, great. So I take an absolute value or just square the two, okay? And I sum up squares of all of these, what we call them residuals, between the actual data and the model. And this is what I'm trying to minimize, the sum of these squares, which is why we refer to this type of modeling as residual square. Why is it important to use the square? Well, if I actually did the absolute, for instance, one example, if I didn't have the square here and I just had the difference, then often positive and negative things would cancel each other. Okay? So that's basically shown here. I would basically, in this case, if I had something like this and something like this, I would get, if I just summed up the differences, so here I'm actually precise, I'm just going through the 2 points that I need, and in this mirror case, I have a positive and a negative error, and those two cancel each other, and both of these lines are equally good in terms of fitting the data. So that's a bad one to use. That's why we want to at least use the absolute values. Okay? Now, absolute values in themselves are hard to work with. If I want to analyze the model, it's hard to do the derivative and all that sense of the absolute value. So square is actually a better way. Also, square as a function is parabolic. And a parabolic functions that is of positive values will have a shape like this, right? So it has a minimum that I can look for. Okay? So analytically, I'm going to get a more unique solution because this parabolic function will give me the solution. So this is basically, and there's all kinds of other ways. If I just try to minimize the maximum distance, for instance, between the two, then basically one outlier point will pull my trend too much to itself. So I don't want that either. This is essentially why we want squares. So squares help us. Excellent. So this is what you've done in your exercise, and I'm going to walk through the procedure. So basically, you had only 2 points, but you could technically have n points, and whatever you've done would actually proceed the same. So my sum of all of the residual squares is given here. Again, my data is xi, yi, so this is simply a number of data points, and this is the difference between the actual y value and that a model would give me for the given xi. And I'm looking for a0 and a1. As ugly as this looks, I know xi's and yi's. Okay, so all of those are just simply numbers that come along and that I have. So when I actually try to minimize this, it's just like in a minimum of a function, right? I basically go and look for derivative. If I had only one function, f of x, I would look, my minimum, I would look for it by setting f prime of x is equal to 0, correct? That's your calculus exercise. I told you you can't run away too far from calculus. So essentially, in multiple dimensions, here I actually have dependence of this SR on two variables, a0 and a1, and I'm looking for a0 and a1. So basically, both of my partial derivatives with respect to a0 and with respect to a1 have to be set to 0. And that essentially gives us the equations to look, this being a parabolic kind of a function, the extremum that I'm going to find is going to be a minimum. Okay, there are no inflection points. This is not a cubic function. There are no inflection points, and there are no maxima if I have a positive function that is quadratic in its behavior. Okay, great. So basically just taking these partial derivatives with respect to a0 and a1 and setting them to 0 gives me the equations. And again, I have some sums, but by now we should be used to using sums. And when I clean it up, in case of n points, what I'm going to get is n times a0 plus sum of all of these x's times a1 is equal to sum of yi's. And this is, again, this is sum of all x's, a0 plus sum of all of xi squares, a1 is equal to sum of all xi's, yi's. What I don't know here is in red. It's a0, it's a1, okay? So I have an n, I know, this sum I can compute, this sum I can compute, this sum I can compute, it's actually the same as this one, this sum of squares I can compute, and this sum I can compute. So everything I can compute, it's a 2x2 systems, okay? 2x2 systems we solve by hand, no problem. And I can actually, by Cramer's rule, if you do remember, did you go over Cramer's rule in your other linear algebra portion of differential equations? Maybe, maybe not. You can come up with equations directly for a0 and a1, okay? And those equations depend on these sums, okay? You could only simply set up a 2x2 system and use any of your favorite solvers to find a0, a1. Either way works. Okay? But since this is a 2x2 system, I can actually just have a directly computed solutions for a0 and a1. And I believe last time you have gone halfway in solving this. Okay? So basically this is, you want to create a linear regression function that takes some vectors and as input and provides the linear fit of these parameters a0 and a1. Okay? If you can find some function, you can use it. You can also just create these sums on your own, either way. So how far along have you come in solving this? What does that mean? Basically, you haven't? Okay. So first thing that I do, I'm just going to copy this data and post it on Canvas just as data so that you don't have to type those in. So let's get going. Open up your Jupyter notebooks. We want to program not just that, but we want to keep going and get some more interesting. Again, and this data is in the slides, but I think it's hard to copy from the slides sometimes. I'm just going to say data for curve fitting. Boom. There we go. All right. Spring2019. Okay. So I'm just going to plot the data. You keep programming with your programming. What you started. I'm going to define so just to yeah. So just to show what data looks like. And let's put stars. There. Okay, those are my data points. Just by looking at the data. Is a straight line through this a good model? Actually, it's not. We're going to improve it. Okay, but we're going to first do the straight model. So my function should take x, y as input, and it should return a0 and a1, right? Yay, I got 2 points on the test, 3 points for correct outline of a function.
You mean that's all I needed to do?
For 3 points, yes. I'm going to go the hard way and come up with all of these sums because I'm old school like that. If you have found a function that does the sum automatically for an array, you can do it. So to come up with sum of xi's, it's the simplest version of the sum we have. I initialize my sum x as a 0. And I just add x or y to it. And I do pretty much the same for all the other sums, which is where cut, copy, paste works. And sum y and sum square. And at the end of this loop, I should have all of the sums completed, right? So then my A0 and A1 are just simply formulas that involve these. And this is the exercise of typing them in correctly. Did anybody type them in correctly already? Okay, you're all working on it. The answer to that is working on it, Dr. Pradhan. Some. Do we agree? Simple enough? Just a matter of typing it in and executing it, right? How do I now test whether I did a good job? What is my model? What is my regression model for this data? It's a line. Line A0 plus A1x. So for all of the x's that I have, I plot a line A0. So that's my model, okay? And it's a functional model, so if I'm using this as a trend somewhere else to predict something else, I have a function that gives me prediction. Does that make sense? All right? So that's, if you were in a reservoir and you fit your porosity permeability data and you have this function that predicts permeability as a function of porosity, knowing permeability as a function of porosity is not easy, right? But you do that for some formation, and then you use that as a functional relationship somewhere else to predict something else. That's the whole point of curve fitting and of predicting trends. Now, all you're doing is extrapolating existing data, so don't be confused about that. It's not necessarily always going to work. But it's better to use some data than not at all, right? Okay, moment of truth. Let's now, I'm actually going to copy this plot and just move it downstairs. So this is basically simple linear regression. And now my model, I'm going to call it Y model, is X A0 plus A1 times X. That's my model data. And I need to first allocate some space for that. So I'm just going to create my vector of zeros in the same size and shape as X. And then I'm going to assign it to be Y model, and then I'm going to plot that too. And I'm going to plot it as, I don't know, red line or line, red line. So this is my actual data. And this is my model. And I need to, what is my A0 and A1? What I gotta compute it. I have a function that gives me A0, A1. It's called linear regression. This is how I call that function. And this is where there will be a moment of truth to see whether I typed in everything correctly. It's simple formulas. Formulas are not complicated. There's plenty of space for typos. And if this line kind of goes through the data, that's going to be my, are we ready? Let's see how my typing is on Monday morning. Well, I have something else. Plot. Not very good. Linear regression of XY, did I? That's how I do call it. Not enough values to unpack. Okay, I can just give it n. Oh. Length is fine. It's complaining because the other one is empty, but it should still give something. NP length of X, that should do it. Save. Now I've done something else. Let's just test it up here. Oh, there's just plain length. No. Oh, just length. All right. So it's not an NP. There was NP length. Okay, never mind. I was pretty certain there was NP length. Now I have something else. No, I don't. So, len of X is a key. The problem it has is this part. The second one is actually empty. So probably if we just say n is equal to X shape, it should recover. Yeah. So one can just do n is equals to without trying to. I thought that it might want to fit that other one.
I don't know if it works as an integer if you do it the way you just did. I tried that, then it's like n times.
Then it's, you can always do int of it.
Oh.
Okay, so that's that conversion. And if it's a sort of a logical that number is, like you don't do int conversion of m character, but if you do it of a real number, it's going to do it without a problem. And it's going to just create an integer version of it. Okay, doke. So did everybody type in their formulas correctly? How was your typing this morning? And then did you get something like this?
I'm still having problems grabbing the first one.
Just graphing or
Yes.
just this part?
Yes, I don't know.
So what is your A0?
My A0 is just mentioned.
So do you get these two values? Print them. So you should get A0 and A1 as these two values. So open up and type in linear regression. Steve, open up the lecture 7. There's a slide with the exercise and start typing in.
I'm trying to Python won't start up.
Oh.
I'm trying to get it to start up.
I got mine.
There's a Monday morning as well.
Yeah.
I didn't get the same A0 values.
So that's where little typos have crept in. These sums, easy one to do is to type in sum x2 instead of doing a square of it. So this is a square of the sum x, okay? That's the most common one. So the most common one is to do sum of squares here, except instead of the square of the sum. Sum of squares and squares of the sum are two different things.
Yeah, she got -5, something like that.
So I'm just gonna quickly post this because I want to move on with the lecture.
This is what I got.
Did you update the file?
So I'm gonna post the file. I never posted it, so I'm gonna upload it right now. There we go. So
CurveFitting or you want linear regression?
CurveFitting is the name of my thing. I named it CurveFitting. We're gonna add to it, so it's not gonna be only linear regression in there. So you can compare it to my file. Just to have something that runs. So, I'm going to say this is not a good model. With linear regression, we can indeed, I'm not going to do it this very moment, type it in, but it's relatively easy to do. So I want some measure of how things fit, okay? And if I have data like on this slide, well, it's slide 12. So if you go and see the data up there versus here, it could be actually the same linear function. It's a very good question. How do I measure, right? How well, obviously the first line fits the data better, and the second line is not that well represented by the data. And I want some measure of it. For linear regression, so there are multiple ways. What I could do is simply come up with what is that sum of residuals and divide it by number of points just to normalize it and use the square root of it. So that's one way to measure. or there's so-called R coefficient. And we're not going to go into deriving it, how this R coefficient I get, but this R or R square is the most used for linear regression. And basically when it's 1, I have a perfect fit. Below 70% I shouldn't go. It's not a good fit, but if I have nothing else, I might still use it. But you have to understand that good fits are basically this R square being 0.8 and above, okay? So it gives me some sort of goodness of the fit. And again, it's relatively easy to program in there. Now I would like to actually move forward and do some better fitting of this. Okay? I don't like how that line just kind of, data seems to be curving. So the simple line model is simply not a good model. But before I go fit, I have to have an idea of what model to fit. And this is key of the curve fitting. You have to try different types of models. Okay? You can't just go and some magic button, the data decides itself what model you should fit. Because you need these parameters, right? And that's the design by the model. So in this particular case, this is obviously a parabolic model. Well, if it's a parabola, I'm going to have 3 parameters, right? ax squared plus bx plus c, abc. Or in this case, we're going to number them, so it's going to be a2, a1, and a0, right? And I could keep going if I want polynomial fits. But polynomial fits are not always good either. So let's say that I want this. I often have data that goes over multiple scales in magnitude, and especially in petroleum engineering or any kind of subsurface engineering. Data often goes over multiple scales. So typically I have to have some sort of exponential models that actually, or logarithmic models that actually capture that. Okay? So one simplest one would be y is equal to a e to the bx. Now, if I proceeded to find a and b, if I looked at those derivatives of the square of the residuals versus a, and then the partial derivative versus b, I would get a set of equations, but they would be nonlinear equations. There's a variant of Newton-Raphson for multiple dimensions that we could employ, but it's not the fastest thing ever. But we can actually be clever and use our linear regression model to fit this data. How? If I take a natural log of that expression, y equals to a times e to the bx, I'm going to have that ln y is equal to ln of a times e to the bx. And I know that I can split multiplication into a sum, so I have ln a plus ln e to the bx, which is bx. Do we agree? A little bit of, what is this, basic elementary math, really. Okay, great. So now, if I look at this, it appears that my natural logarithm of y and x, so I have original data x and y, and it seems that natural logarithm of y and x are technically in a linear relationship. Do we see that? This is my coefficient, what used to be a0, and this is my a1. Yeah? So I can transform my data and basically look for these linear coefficients. Let's call them uppercase A0 and uppercase A1. Okay? And figure out afterwards, when I fit this, figure out what A and B should be. Can you use either your or my linear regression code to do that with the same data? Oh, apparently. Yeah, we can try. This one is not going to work. This one is going to be better with the data. But it doesn't matter. Let's try to fit it. Maybe it's good, maybe it's not. So again, you have to use linear regression with x and logarithm of y. And that's going to give you two parameters. But then you need to relate those two parameters that you get when you fit this to a and b. Take a piece of paper if you need to. Does this ring a bell? So I'm using the same function that I had. I have a function that gives me a linear fit. I'm just changing the type of data I give it. Because this conversion gives me a license to do so.
Close your parentheses.
Now, thank you. Now my new model is reportedly this a times exponential of b times x. But my only problem is what are a and b? What are a and b from this linear fits uppercase A0 and uppercase A1? Elementary calculus or mathematics or algebra or whatever you want to call it. So my A0, yes, A0 is logarithm of A. That makes A exponential of A0, yes? And what is B? Oy. This is A0 plus A1x. B is A1. Yeah, it's actually simple. Now I have no clue whether this works well, so let's see. So I'm just going to plot this Y model too. And I need the data somewhere too. I'm going to do this with green. Oh, I did something else. Oh, shape. What else did I do? B times X. I'm typing and talking in parallel. Is always producing some fun times. Okay. A little better. But I'm not too happy. I had here B of X for some mysterious reason, and it's B times X. I can't tell you why. I was just talking and typing. Now that we're here, did everybody get this relatively good fit? Curving a little more. If your linear regression didn't work well to begin with, then this is not either. But that's why I posted mine.
Mine says linear regression.
You need to execute that cell.
I need to execute all of them.
Right.
So all I do is just open it.
Okay. Cool. Well, now that we're at it, let's try this one as well. Okay. And in this case, if I take log of this expression, then log of y is log of a2, and my parameters are a2 and b2. How I call parameters is irrelevant. I just don't want them to be the same name as some previous ones. Times what ends up being b2 times log of x, right? So now I would actually fit what is in linear relationship? Log of y and log of x, right? If I take this as new variables, my new variable, call it y tilde, is log of y, and x tilde is log of x, then two of them are in linear relationship. This is still a number, and this is another number. So number plus number times x, right? Great. So now let's do that fit. Maybe it's going to be better. I'm just going to do cut, copy, paste, and do modifications. So I'm going to call these still A0 and A1, and I'm going to do NP log of X and log of Y, okay? And then my relationship between the two is a little more, so I'm going to call them A2 and B2. So my A2 is NP log of A0, and my A1 is still, B2 is still A1. If you just give me literally 3 seconds, my model is now A2 times X to the B2. And I just like putting extra things. And now I'm going to plot my model 3. And a better fit. This is a good fit. There's an outlier here. I'm not going to get better fit than this. Yeah? So relatively small change. Okay? I want you to finish these two fits, exponential and the other exponential. Okay? And submit that as a quiz. Okay? So I want these 3 plots.
Can we put them all in the same slot?
Yes, that would be great. So if plot extra points for putting them all on the same plot to see how well, and annotate the plot nicely. So it's immediately visible which one is the best. Yes? Legend? Use legend.
For the project, you said?
Huh?
For the project, you said?
No. So here, this is going to be a little quiz,
Okay.
finishing this up, right?
Oh.
So either 3 separate plots, but it'd be great to have them all on one to see how well they fit. Yes? Yes.
But you won't post it on the codes.
I'm not going to post this code. I posted the linear regression. That's what you're using, right? The core code is posted.
So we need to do
So all you need to do is this basically.
so
How do you linearize your nonlinear relationship? Okay? By taking logs of sides, this is what I've been doing. And the recording of this is going online, so there's that.
So we need to do also the cross multiplying and so on. So the third one, right? So we also have to do the third one, right? The cross.
Yes. So this one and this one. This one, no. No.
Okay.
I don't think, you can try. I think it's going to be pretty poor, but that's up to you. If you'd like, go for it. May as well. It's really cut, copy, paste, and a little bit of, yeah? Again, the key thing is that you have to know model you're fitting. And some of them you can linearize. The joke goes, if you cannot use one of the power models to fit your data, you haven't tried hard enough.
When is this due?
On Wednesday.